Hey everyone, and welcome. We use these incredibly complex devices every single day. Our phones, our laptops, but have you ever stopped to think about what's really going on inside? Well, today, we're going to peel back the layers and find out that it all boils down to some surprisingly simple secrets. Let's get right into it.
I mean, just think about that for a second. How does a machine that's basically made of sand and lightning think? It sounds like something out of a sci-fi movie, doesn't it? How does it calculate things, stream videos, and connect to the entire planet? Well, that's the big mystery we're going to unravel today, and we're starting right from the ground up.
Okay, so you look at a diagram like this, and yeah, it seems like an impossible maze, right? You've got all these boxes, CPU, memory, I/O, it's a lot to take in. But what if I told you this entire city of logic is built on the simplest idea imaginable? A single switch that's either on or off. That's it. So to understand how that simple switch can lead to something like a thought, we first need to learn the language it speaks. And the good news? It's an alphabet with only 2 letters. So that basic on-off state, it has a name. It's called a bit, which is just short for binary digit. We just represent off with a 0 and on with a 1. Seriously, just think of it like a light switch. And here is the absolute key. Every single piece of information inside a computer, no exceptions, is built from these simple little switches. So what does that look like? Well, this long string of ones and zeros you're seeing, that's just a computer's way of saying, hi. Every letter you type, every color in a photo, every sound in a song, it's all just a very specific pattern of these simple bits. Okay, so just having a language isn't enough, right? You need something that can actually read it, process it, and do something with all those ones and zeros. So let's meet the tiny workers that make it all happen. These things are called logic gates. Now, don't worry about memorizing all these different symbols. What's important to know is that they're all super simple circuits. They take in 1 or 2 bits, they follow one simple rule, and they spit out a single bit as an answer. You can think of them as tiny, perfect little decision makers. All right, first up, we've got the AND gate. This one's the strict one. It will only give you a 1, an on signal, if the first input and the second input are both 1. If even one of them is a 0, nope, the output is 0. That's its only rule. Then you have the OR gate. This one's way more laid back. It'll give you a 1 if the first input is 1, or if the second input is 1. Heck, it'll give you a 1 if they're both 1. The only possible way to get a 0 out of an OR gate is if both inputs are 0. And last but not least, we have the NOT gate. This one is maybe the simplest, but it's also one of the most important. It does just one job. It flips whatever you give it. You send it a 1, it spits out a 0. You send it a 0, you get back a 1. It's the ultimate opposite machine. So we've got a language made of bits, and we've got logic gates to make decisions with them. But there's a problem. Those decisions are gone in an instant. The next big hurdle is figuring out how to give our machine a memory. This is a really cool puzzle to solve. I mean, logic gates are all about the here and now. What are the inputs right now? They don't have any idea what happened a millisecond ago. So how do you get a circuit to actually hold on to a value, to remember a 1 or a 0 even after things change? The answer is actually, well, it's beautiful. You just take the output of a circuit and you feed it right back into the input. You make a loop that can hold a signal all by itself. And this is what that loop looks like in real life. It has a kind of funny name, a flip-flop. Now, don't get lost trying to trace the lines. The genius of it is just that by wiring a few logic gates into this feedback loop, you create a circuit that can be set to 1 or reset to 0. And, get this, it will hold that value. It will stay that way until you tell it to change. This right here, this is the very first atom of computer memory. Okay, so this is huge. We now have our 2 fundamental building blocks. We have logic gates that can think, and we have flip-flops that can remember. Now we can start snapping them together like they're digital Legos to build pretty much anything we can imagine. And the plan for building is surprisingly simple. Step 1, you arrange your logic gates to do a specific job, like adding 2 numbers together. Step 2, you use your flip-flops to catch and hold on to the answer. That's really the core idea behind everything else. So let's look at a quick example. This diagram might look a little crazy, but it's really just a handful of those AND and OR gates we just talked about. When you wire them up in this particular way, you create something called a full adder, and its only job is to add 2 bits together and figure out the sum. This is how a computer does math at its most basic fundamental level. And now we can see how things start to scale up. You can see how these simple blocks combine. On the one hand, you have circuits like our adder, made of logic gates for thinking, and on the other, you have circuits like this 4-bit register, which is really just 4 of our flip-flops put together so it can remember a 4-bit number. You just keep combining these simple thinking and remembering circuits to build bigger and more powerful parts.
All right, now that we've got all our Lego pieces, let's zoom back out and take another look at that super intimidating diagram from the beginning. I promise it's about to make a whole lot more sense. So, here we are again. You see that big box labeled CPU, the central processing unit? Well, that's just millions and millions of our little logic gates. And that box for memory? You guessed it, that's just millions and millions of our little flip-flops. Everything on this chart, no matter how complicated it looks, is just a giant, really clever arrangement of those simple thinkers and rememberers we've just learned about. So let's just recap the journey real quick. We started with the bit, just a simple on or off switch. We gave it the ability to make decisions with logic gates. We gave it a memory with flip-flops, and by snapping all those together, we built the bigger components that make up the entire architecture of a computer. And that really leaves us with one final, pretty mind-bending question. If everything your computer does, from simple math all the way to artificial intelligence, is ultimately just the result of billions of simple switches making simple decisions and remembering the outcomes, what does that imply about the complex thoughts happening inside our own heads? It's something to think about. Thanks for joining me.